Stresses occur in all structures subject to loads. If an external force acts on a beam, there is always stress acting on it. To see what it looks like, let's cut the beam by an imaginary plane. If you remove one part of beam, you can see how the average stresses develop.
In this video, I will derive these three equations, which are the equilibrium condition equations of any stressed body. A stressed body is basically a body which is being applied any external force, and those external force are giving rises to certain resistive force inside the body, and under those conditions we apply these three equilibrium conditions. These three equilibrium conditions are basically important because when any body is under its plastic limit, so we consider the body to be stable, and when we consider the body to be in stable condition, then by applying that this, which is delta of fx equals to 0, we get this condition. Similarly, by applying delta of fy equals to 0, we get this condition, and similarly delta of fz equals to 0. After applying these conditions, we get these equations. So how these equations are being derived, I'm going to prove this in this video with the help of lot of pictorial views. So in order to derive this three equation, one of the important formula that we must know is that of the stress gradient. Stress gradient is basically the variation of the stress with the distance, and hence the name suggests stress gradient. For example, this formula says like this. Okay, let us take me an example and then say it. So for example, we have a body under consideration, and suppose at this point the stress is say sigma x. So at this point the stress is known to us. Under when this body is under application of any external force, then it will have stress, and suppose at this point we know the value which is sigma times x. So in order to know the value at any distance, suppose say delta x from the origin, so at this point the stress will be given by this formula which says sigma times sigma of delta x is equals to sigma times x plus del of sigma x by dx into delta x, which is actually the distance from the origin or from the point under consideration. Now suppose we have a let us start the derivation. Suppose we have a body, say like any random shaped body. So this body, if we apply any external load in it, says we are applying external load f1 in this direction, say f2 in this direction, or say randomly f3 in this direction. So under the application of this various load, if we take into consideration any internal body or internal surface inside this body, it will have some sort of resisting force inside it, and those resisting force will give rises to these derivation of these three equations. So let us draw the internal part of this body here. So the body is something like this. So after cutting the cross section, we have taken this below cross section, this part under consideration. So we have taken this out here. So under the application of this external forces, we will have any random so small f1 in this direction resisting force, small f2 resisting force in this direction, small f3 resisting force in this direction. We will have all this force. And now suppose we take into consideration a small area here. If we take into consideration a small area in it, so while this body is in equilibrium condition, not in equilibrium condition, this body is in stable condition under the application of this loads. So we are taking into consideration that inside the elastic limit of the body, the body will be in stable condition. So this internal cross section area here will also be stable. So all the forces which is being acted in this small infinitesimal small area here inside the body, they will be equal in nature. Otherwise the body, if the forces would not have been equal in nature, then the body would have broken down, or it would have deformed drastically. So all these cases are not occurring here. We are considering that the body is inside its elastic limit, so the body part will be in a stable condition. And now if we take this say let us draw it here. If we take this small infinitesimal area here with all the edges intact, so this is the small infinitesimal area, and this f3 force will have three components, one along this direction, say this is to be f of z, one along this direction say it have to be f of y, and one along this direction say it to be f of x. So all these forces will give rise to a strain inside this body and shear forces inside this body which we will equate in the following page to get this above three desired equations that we are going to prove in this video. So this is the small cross-sectional area that we had got from our previous picture. There we had taken a body and applied the external force, and then after cutting the body we had analyzed the internal forces, and then we had taken out this area. So under the application of that internal force, this small area we actually I had exaggerated it, so I had making it a bit larger. So actually this is the length, its length is dx, and this length is dz, and this actual length is dy. So these are the dimensions of the small area, and because I had exaggerated it, so that's why I had made it a bit larger, or a bit in a greater way. So under the application, and if you have remembered, there was an internal force which was acting like small f3 in this phase of the small infinitesimal area. So this internal force or the resisting force will have three components, and those three components will give rise to various stresses in the different directions. So suppose let us analyze that this f3 small or this resisting force have the component fx plus fy plus fz. These are the three components which are coming from this internal forces or the internal resisting force. Now this fx will give rise to a stress in the x direction plus torque, shear torque actually, in y direction plus a shear stress in z direction also. So before going to make these forces pictorially, I want to make you familiar with this subscript, what this means. So tau of xy means, the first subscript means in the plane perpendicular to which our force is acting. For example, here what does this mean? Tau of xy means a force which is acting in a plane perpendicular to the x direction and along y axis. So first subscript, which means plane perpendicular under consideration, and this y second means force along which direction. So if I want to say the entire thing, what does this denote? So a shear torque or a shear stress which is acting in a plane perpendicular to the x-axis and along the y-axis. So if I want to suppose this is our plane, and now for this plane only I am considering this to be x-axis, this to be y-axis, and this is to be z-axis. So if a force, suppose this is the shear force which is acting along this direction, now this tau xy, how can we denote it here? So tau x means a plane perpendicular to the x-axis, which means this is our plane under consideration. So in this plane the force is acting along, or the shear force is acting along the y direction. So this will be the directions of the tau xy. And similarly here, a shear force which is acting in a plane perpendicular to the x-axis and along the z-axis, so it will be like this, tau xz. So these are the meaning of the subscript that I want to make you clear before I proceed ahead. And I am going to analyze each phases, means I am going to first analyze the x direction, means basically the equilibrium conditions that I am going to derive. I am going to derive it by making the drawing of each individual phases, not in a single drawing. So first I will analyze the x-axis, then the y-axis, and then the z-axis. So because all the three cases are this familiar, so first I will derive the x, and both other y and z will be similar to it, so I will not derive it. I will first elaborately derive the x-axis, and that will be sufficient for the y and the z-axis also. So here in this before starting the derivation, I want to show you that under the application of this internal force on the infinitesimal small area dA, all the sides means all these sides. Let me make the coordinate axis so that it will be more clear. So this is the x-axis, this is the y-axis, and this is the z-axis. So in this figure we can see that the body has little bit extended in this x direction, in this y direction, and as it is a bit difficult to show that it has also extended in the z direction, it has actually extended. I am not able to show here so clearly. So here you can see that this body has little bit extended in the x direction, which is denoted by delta x. It has extended a little bit in the y direction, which is denoted by delta y, and similarly in the back side it has also extended, which can be denoted by delta z. So these are the things which we are going to take help of in the derivation. So as I had already shown you in the starting of the video that the under the application of any force, if a body is under a stress condition, and if we know the internal stress at a given point, so at a distance, suppose delta x, it can be written as sigma times x plus del of sigma x times dx into del x. So here we are going to take help of this. Delta x will be this delta x, and similarly in the y and z direction will be this delta. Now till now we have seen that how the under the action of the internal forces on a small area dA have its three components, and now I had told that I will discuss the shear stress and the shear strain components only along the plane which is perpendicular to the x-axis. So let me denote the axes that I had taken into consideration for this small area. So this is the x, this is the y, and this is the z axis. Now in the for originality, after the action of the internal shear forces, the what will be left out is what will occur to this plane which is under after the exaggeration by a length of del x. It can be written as sigma of x plus del of sigma of x by dx into del of x. Now similarly the strain which will be acting in this plane will be tau of x y, because tau of x means in the plane perpendicular to the x directions, and y is because under the direction in which the force is acting, plus del of tau of x y by dy because it is in y directions, into del y because del y is the elongations in the y direction, and similarly the z component will be tau of x z plus del of tau of x z by dz into del of z. These are the value of the shear stress and strain which we had written on the basis of the stress gradient formula, and corresponding to this what this will be the shear stress in the opposite directions for each component. So this will be tau of x y. Take a look, this is in the opposite direction of this expansion. So similarly the z will be like this, tau of x z. So now after writing the direction of the shear stress and the shear strain on the plane which is perpendicular to the x direction, we can write this condition which is del of f of x equals to 0, because this condition we are able to apply here because they under the action of this, we are the assumption that we had taken that under the action of the internal forces the body is in elastic limit, and so within the elastic limit we consider the body to be stable, and in order to maintain that stability we assume that in all the direction of a small area, that is dA, that we had taken into consideration will have this condition, that is delta of f of x equal to 0, delta of f of y is equal to 0, and delta of f of z will be equals to 0. All these three conditions must satisfy in order to ensure the stability of the material. So now as we are looking into the x direction, so after breaking these forces we can write like this: sigma of x plus del of sigma of x by dx times del of x multiplied by this force is acting. And one more thing I want to mention, that this length is del x, this length is del z, this length, and this length where I will write, yes, let us write here dy, let this be the dy. So this force, how we can write force can be written as as we know, pressure is equal to force per unit area. As these are the pressures which is acting here, so we can write the force to be pressure times area. So this is the pressure and the area will be dy times dz. So this will be dy times dz minus this del x. So del x, and here the area is also dy times dz. Then another term will be, let us consider this shear stress, which is tau of x y plus del of tau of x y by dy times del of y, and this is acting perpendicular to this area, that is del x and del z. So it multiplies by del x times del z minus this shear stress, that is tau of x y. This will the same area del x and dz. Another term will be this term along the z direction. What is the shear stress? That is acting tau of del z plus del of tau of x z divided by dz times delta z. And here the area will be, you will look that this is dx times dy, because this force is acting in this direction which is perpendicular to this area, which is dy times dx. So dy times dx minus tau of xz times dy times dx. Now after eliminating certain terms from here, we can simplify it. For example, let us take a look. Like here, if we put this thing inside the bracket, del x dy dz, and here it is minus, so these two terms will get cancelled out. So finally we will have del of del x by into del x, this will be divided by del x into dy dz. Similarly, in this term, when dx dz will get multiplied to tau of xy, here we have its negative term, so these two terms will get cancelled. We will left out with only this term, that is del of tau of xy divided by dy delta y into dx into dz. Similarly, this term here, this term will get cancelled out with this term, so we will left out it with only del of tau of xz divided by dz into del z into dy dx equals to 0. So here if we take out common dx, dy and dz from all the terms, this is delta x can be simply replaced by dx, because both these things denotes the same here. As here the delta is very small for us, so we can also replace it by d. So here we are also getting dx dy dz, here also we are getting dx dy dz, here also dx dy dz. So if we take out common this thing, so we will be left out with del of sigma x by dx plus del of tau of x y by dy plus del of tau of x z by dz equals to 0. So now this is the we can say this is the volume of the small cube that we had taken into consideration. So that volume can't be 0, because that is a physical thing which is existing there. This can't be 0, so obviously this term will be 0. So by putting delta of x, f of x equals to 0, the conditions that we are getting, del of sigma x by dx plus del of tau of xy by dy plus del of tau of xz by dz to be equals to 0. This is the thing that we were wanting to prove from the starting of the video. And similar to this, we can analyze the forces in this plane which is perpendicular to the y-axis, or this plane which is perpendicular to the z-axis, to find out the same equation with the help of the simple terms of forces. So I hope that you all understood it. If you like, please do like, share and subscribe, and thank you for watching it.